Third solution. Earlier, we used the variable x to represent the distance of the base from either the apex or the center. But this time, let's use x to represent half the base. Now, of course, now I realize there's another solution that somebody could have come up with. That's a solution where you use x to represent the entire base. That's something that you guys could explore. But before I proceed, let me point out that this was this solution I'm presenting is based on one student's email. He asked me if his solution was correct, and I don't want to fully identify him because I don't want this to get to his head. He might, many years down the road, tell his grandkids that when he was a first year student in Ateneo, his solution was immortalized in a YouTube video, and we don't want that to happen. So I'm not gonna call him by his real name. Let's call him Maulo Panansala. That's all I'm gonna say. No further credit will be given to Maulo Panansala. Okay, so let's use x to represent half of the base, and the interval is 0 to r. So let's try to illustrate. All right, these uh, varying possibilities for the value of x. So here is an illustration of x becoming smaller. Of course, strictly speaking, x never becomes 0, or else this triangle ceases to be a triangle. But okay, x never becomes 0, and then x is at most r because, well, the base can be no longer than the diameter, so therefore x can be no longer than the radius of the circle. All right. There's one thing I'd like to point out, because the usage of this x, a particular value of x, can be shared by um, two triangles. So what I'm saying is that this blue triangle has a twin, all right? And so that's a twin. All right, I forgot to mention that this black segment would be, by the Pythagorean theorem, the square root of r squared minus x squared, so making the height r plus the square root of r squared minus x squared. But before we go to the error formula, all right, I wanted to point out the complication with having a twin. All right, so the twin is a triangle with dotted blue segments. And so why is it a twin? Definitely not an identical twin, but rather a fraternal twin. So it's a triangle having the same base. And because the base is the same, then it shares the same x value shown here in green. So it complicates things a bit because, for example, if I tell you, oh, okay, the triangle with the largest possible area is the one for which x is equal to 1. But then which triangle is that? Because then you have these two triangles having the same x value equal to 1. But clearly, as you can see from this illustration, one of them would have a smaller area and one of them would have the larger area. And because they have the same base, all right, and the problem is asking us to find a triangle with the largest possible area among those inscribed in the circle, which are isosceles. All right, if you pair up all these twins, with one of them having the smaller area and one of them having the larger area, then it suffices to take only the twin with the larger possible area and ignore the one with the smaller area. All right, so it's fine to consider only the larger triangle in terms of area, but what would that mean? Well, the triangle with the larger area in each twin pair would have to be the triangle with the larger altitude, the longer altitude, which means that the base would have to be lower than the center, as you can see here. All right. So the base is beyond the center from the apex. So let's agree on that. So in other words, even though in my illustration I could bring this movable blue point much higher, All right. So you can see the twin now is the one with the dotted twin would have the larger area. Let's assume that we can't go higher than the horizontal diameter. All right. So that means this blue point will only have to go lower. All right. So just so there's no ambiguity. Alright, so we're going to take only the triangle with the larger height. So now it's clear, we could proceed. The height is that r plus the square root of r squared minus x squared. And then since the base is 2x, then we've just identified the height. Then we have this formula for the area. Alright, so the 2's cancel. And then let me distribute the x. So that's what you're going to get. And then let's use the usual differentiation rules. A prime, so from Rx you get R. And then x has the square root of R squared minus x squared. To avoid the product rule, you could move x inside as a factor of x squared, multiplied to R squared minus x squared. Or, so we don't forget the product rule, verify that the second and third terms are the results out of the product rule. Alright, now to find critical numbers, let's clean this up a bit. For example, cancel the 2's and then combine everything under the same denominator. This is what you should end up having. Pause the video if you need to verify. Alright, now, alright, what are the numbers in the domain for which this is undefined, for which the denominator is 0? That's only going to happen when x is r. Remember, the domain is 0 to r. And then when is the derivative going to be 0? When is the numerator going to be 0? That's going to happen when r times square root of r squared minus x squared is equal to the second and third terms move to the other side, which is 2x squared minus r squared. To solve for the value of x, let's square both sides. So I can verify that. And then cleaning things up reduces things to 0 equals this fourth degree polynomial. After factoring x squared, you get this. So that's going to happen when x is 0, or when this second factor is 0. So when you solve for x, there's a positive and negative square root, but because the domain is 0 to r, then you only need the principal square root. So that's square root of 3 over 2 times r. So just like before, all we gotta do now is evaluate the area function at the endpoint 0 and r, and at our critical number. So this is the area formula. These are what you're gonna get, and it's clear that the last area computation is the absolute maximum. It's the same area as before. Now, again, don't forget to answer the question, what are the dimensions, which we've already identified from the previous two solutions. I just wanted to point out that in case you're doubting whether this really is the larger area, well, if you approximate that coefficient, it's larger than 1. So this is really greater than the second area, A of r equal to r squared. And then, so the height is, as we already identified it earlier, r plus the square root of r squared minus x squared. If you plug in this critical number, that would reduce the height to 3/2 r. And then the base is this 2x, so double our critical number, square root of 3 times r. Same conclusion, the triangle should be equilateral.